Hello and welcome back to the course on deep learning. I hope you enjoyed the introduction into RNNs. And today, right away, off the bat, we're going to jump into a huge problem that exists with RNNs. All right, so what is this problem called the vanishing gradient? It was first discovered by Sepp Hochreiter, and I hope I'm pronouncing that right. I know we have students from Germany, so you can comment if the pronunciation is incorrect, but Sepp or Joseph is his full name, is a genius scientist who back in the 90s, while he was still, not a professor, this is a recent photo, so he was much younger when he actually came up with this concept, he found that there's a big problem, and we'll talk about the problem itself just now. I just wanted to point out who are the people that spotted this, and basically, as you'll learn from the further tutorials, Sepp is one of the founding people in the modern way that we use RNNs and LSTMs, and we'll talk about that further down. But this is Sepp Hochreiter, so I just wanted to make sure you know who is behind all of this. And the second person is Yoshua Bengio. He's a professor at the University of Montreal. He also discovered that this problem, I think a bit later, 1994. So Sepp was discovered this in 1991. Joshua wrote about this in 1994. But again, this is another person driving this whole, pushing the envelope in the space of RNNs. And if you go to the University of Montreal and you look up Joshua's profile, you will find that Yoshua has over 500 research papers. And by the way, there's Yoshua Bengio just hanging out with Jan LeCun. As you can see, they all know each other. It's a very tight-knit community, and it does sound like a conspiracy. These people that are driving or pushing the envelope in terms of deep learning, these are just like a select group of people who are all in it together. They all know what's going on. They've all been doing it since the 80s or 90s, and now it's all popping out into the world. So there you go. That's just to give you a quick idea of who's behind all of this. And now we're proceeding to the vanishing gradient problem itself. So as you remember, this is the gradient descent algorithm. We're trying to find the global minimum of your cost function, and that's going to be the optimal solution, optimal setup for your neural network. As you also recall, your gradient or your information travels through your neural network to your answer to get your output, and then the error is calculated and is propagated back through the network to update the weights. And here we've got some weights written out. So what happens in a recurrent neural network is a similar thing, but here you've got a bit more going on, right? So when your information travels through the network, it travels like that. You've got lots of it travels through time, and information from previous time points keeps coming through the network. And remember that every node here, it's always very important to remember for neural networks that every single node here is not just a node, it's a representation of a whole layer of nodes. Remember, we're looking at from the top or from the bottom. They actually extend through this chart down there into this presentation. You can see there's lots more neurons behind the ones that we can actually see, because each one represents a layer. Very important to remember that. And so at each point in time, you can calculate your cost function or your error. So basically, your cost function compares your output, which is in the red circle, to your desired output, to what you should be getting. And this happens during the training. And you have these values throughout the time series. So for every single one of these red circles, you can calculate the cost function. And let's focus on one, just to understand what's going on. Let's focus on this one specifically at time t. So you've calculated the cost function, epsilon t, and now you want to propagate your cost function back through the network. How is this going to look? Because you need to update the weight. So every single neuron which participated in the calculation of the output associated with this cost function should have their weight updated in order to help it better calculate the output, to minimize that error. And the thing here is that it's not just the neurons in directly below epsilon t, directly below this red circle. It's all of the neurons that contributed. And there's many more of them. There's all of these neurons as far back as you go, depending on how many time steps you take. You might take 1 time step, you might take 2, you might take 50 time steps, depending on how you set up your network. And this is where the problem lies, that you have to update, or you have to propagate all the way back through time to these neurons. And when we talk about time, it's not that the problem is that we can't travel through time, not at all. We've unraveled this network, so this whole propagation can be facilitated. The problem lies in something else. And as much as I don't like putting math on the slides, on the intuition slides, we're not going to go through this math, but I'll point out one thing here. So this is the math behind RNNs, and we'll definitely direct you to more additional reading, which you can do to upskill on all of these maths. So here we've got WREC, and WREC stands for weight recurring, and that is the weight that is used to connect the hidden layers to themselves in the unrolled temporal loop. And as you can see here on the left, in order to get from xt minus 3, from this layer, remember this is a layer, to xt minus 2, you need to apply WREC. Then from here to here, apply WREC. And in simple terms, in intuitive terms, what you're doing is you're simply multiplying the values here. As you remember, to get from one layer to the next, we multiply the output by the weight, and then we get to the next layer. And then we multiply the output by the weight and get to the next layer. Then we multiply the output from here by the weight, get here. And the thing here is that we're multiplying by the same exact weight multiple times, as many times as we need to go through this temporal loop. And this can be set. You can set this in your network. Do you want to do it once? Do you want to look back 1 step? Do you want to look back 3 steps? Do you want to look back 50 steps? But as many times as we do it, we have to multiply by the weight. And this is where the problem arises. Because when you multiply by something small, your value decreases very quickly. And the multiplication comes from this p here. You can see that p stands for multiplication, so we have to multiply, and that's what it's representing, that as far as you go back, you're multiplying. And as you remember, weights are assigned at the start of your neural network. As you see in the practical tutorials, your weights are assigned at a random value, but random value is close to 0. And from there, the network trains them up and identifies what they should be. But if you start with a random WREC close to 0, then because you're multiplying by it many times, the more you multiply, the lower the value gets. So if you start off, you might have a certain gradient going through your network, being backpropagated through your network. Then you move backwards, your gradient becomes less. Then your gradient becomes less. And then your gradient becomes even less. And what does that mean for the network? And this is the important part to kind of like get your head around. That what does a vanishing gradient like that, why is it bad for the network? Well, because the gradient, as it goes back through the network, it is used to update the weights, and we know that already. Well, the lower the gradient is, the harder it is for the network to update the weights. It cannot, it can still understand what kind of contribution each of these outputs has towards the error, and therefore it can update the weights, but the lower the gradient, the slower it's going to update the weights. And the higher the gradient, the faster it's going to update the weights and get to the final result. And so, therefore, if you have, like, for instance, 1,000 epochs, these weights for this layer might be updated towards the end of the 1,000, and you'll have some final results. But these weights, because the gradient is so much smaller, they're going to be updated slower, and therefore, by the end of the 1,000 epochs, you might not have the final results there, and therefore, this part of the network is trained, this part of the network is not trained, based on this cost function. But the problem here is not just that half your network is not trained properly, but also that these weights, or this layer, its outputs are being used as inputs for further layers. So the training here has been happening all along based off of inputs that are coming from untrained neurons, untrained layers. So it's kind of like a vicious cycle. You're training here and you think you're getting good results, but because your gradient is so small here, this is training so slow, and the outputs it's giving is so are incorrect, are not final outputs, and therefore you're training on the non-final output. So because of this disbalance, because of vanishing grading, you have a a problem in your network, which is not just that these weights are not being trained properly. The whole network is not being trained properly because these weights are not being trained properly. And that's there's like a domino effect like this. Wherever you look in the network, always the ones at the very back are going to have that problem. And this is, in a nutshell, what the vanishing gradient problem for recurrent neural networks is. And that was kind of the main roadblock to using recurrent neural networks. And let's summarize this in a short slide. So if WREC is small, then you have a vanishing gradient problem. If WREC is large, you have an exploding gradient problem, because same thing, but then it's just going to explode. And here, an important thing to point out here is that, of course, there's more to it, right? There's, as you can see, there's in this formula, there's other things like the activation function and so on. So it's not as simple as small or large or less than 1, greater than 1. But as a rule of thumb, if you have very small weights, you're going to have a vanishing gradient. If you have very large weights, you put 100 in there, the value of 100, then you're going to, by step 2, you're going to have 10,000. By step 3, you're going to have 1,000,000. So then you have an exploding gradient problem. So hopefully this summarizes the exploding gradient problem on an intuitive level, because in short, because you're unraveling the temporal loop, the further you go through your network, the lower your gradient is and the harder it is to train the weights, which has a domino effect on all of the further weights throughout the network as well. And so how do you combat the vanishing gradient problem? There's a couple of solutions. For instance, for the exploding gradient, you can have truncated backpropagation. So you stop backpropagating after a certain point. But as you can imagine, that's probably not optimal, because then you're not updating all the weights. But if you don't stop, then you're just going to have a completely irrelevant network. So it's better than the original approach. Then you can have penalties. So you could have the gradient being penalized and being artificially reduced. You can have gradient clipping. So you could have like a maximum limit for the gradient. You could say never have the gradient go over this value. And then if it's over that value, it just stays at that value as it propagates further down through the network. You can have, for the vanishing gradient problem, you have certain other solutions. You have weight initialization, where you are smart about how you initialize your weights to minimize the potential for vanishing gradient. You can have, there's a type of network called the echo state networks, and we're not going to talk about that, but they do somehow solve that, or they are designed to solve the vanishing gradient problem. But there's also a different type of network called the long short-term memory networks, or the LSTMs for short, which are extremely popular, which are considered to be the go-to network for implementing recurrent neural networks. And that's exactly what we're going to be talking about in the rest of this section. So that's going to be very exciting. We're going to look at a brand new architecture for recurrent neural networks. I really can't wait to get started on that. It's a very interesting topic to get into. But for now, this brings us to the end of the vanishing gradient problem tutorial, and some additional reading. So additional reading. You can definitely reference the original works by Seth Hochreiter and Yoshio Bengio. So this is Seth's paper from 1991. It's completely in German, so I'm not even going to read the name. But if you understand and can read German, then definitely this could be a good read for you. Then there's Yoshio Bengio's paper, which is called Learning Long-Term Dependencies with Gradient Descent is Difficult, 1994. Also, you can reference that. But what I would recommend looking into is a paper called On the Difficulty of Training Recurrent Neural Networks by Razvan Pascanu. It's just newer. It's 2013, and it's also got Yoshio Bengio as the co-author, so probably he was supervising some of this research. And here it summarizes a lot of the things that Yoshio Bengio talks about in his paper from 1994. So why not look at something newer? I would recommend checking this paper out. So there we go. That's the vanishing gradient problem. Hope this was fun. Can't wait to see you on the next tutorial, and until then, enjoy deep learning.